Yep. Okay. All right. So day one exercises. These stuff. So this stuff I know relatively well. I can't say the same for the next few days since I don't know, they're sort of out of my specialty a little bit, but I'll try my best. But today I think we're relatively well covered. Okay, you can all see this, right? This is good. So Scott's theorem, you want to show, for example, the assumption is you have ultrafilter U on some set X, right? I might write kappa from time to time because that's what goes on in my head. And then you want to look at the structure, the ultra power of V by X, and then divided by this ultrafilter U. And the claim is Vx. So this ultra power is well-founded if and only if U is countably complete. Right. So it's omega-1 complete in the exercises, but it's the same thing, right? It just means any countable sets in the measure, you take intersection, whatever you get still in the measure. Okay, so proof. So one direction, let me think. Okay, now this direction. Let me do this direction first. Right. Suppose not. Right. So this means that this structure is not well-founded, so we can fix counterexample. CE means something else in logic. Sorry. Fix counterexample. Right, things in here are equivalence classes to functions. Let me write Fn. You fix countably many functions. Forming an infinite descending chain. Whereas membership here refers to membership in the ultra power. Okay, so what you do now is you consider the intersection. So you got this infinite descending chain. You ask, well, what makes this infinite descending chain true in the ultra power? Well, you take witness, which is here, these guys. Right, you consider this set. Right. Now for each n, this is, so for each n, this set is in U, right? Because this is what makes that true. Just by definition of truth in the ultra power. But this is countably many sets in the measure. So by countable completeness, this cannot be empty. But then fix any I in this set. So call it, I don't know, A. So for any I in A, we're going to have f n plus 1 of I is an element of f n I for all n. Right, so you effectively, what we've done this proof is you translated an infinite descending chain of this star membership to an infinite descending chain of this real membership relation. So this is a contradiction. It contradicts the academic foundation. So yeah. Okay, other direction. Again, it's a similar construction. Right, so suppose let me see. Let's prove the contrapositive. So we want to show what do we want to show? We want to show that if U is not, so if U is not countably complete, then this structure ultra power is ill-founded. Right. Really, it's the same trick. So you wanna suppose you fix xn and omega, fix a counterexample to the countable completeness such that the intersection is not in U. So all of these guys are in U. Now, so fix a counterexample. And what do you do? So if something fails to be in these guys, then they get out at some finite stage, right? So we exploit this feature. So we define a function. So let me think. So for each k natural number, so for each we define a function gk, which goes from your base set to v by saying something like gk of I is, do this by cases, n minus k if n is greater than k, and I is let me think, in this set minus xn. Okay, and 0 otherwise. So basically you want to create an infinite descending chain in the ultra power. So now we observe for all k in omega, the following holds. So we have I next. So right, this it's not very straightforward, but it's a little bit tedious to check, but this follows from the definition of GIs. And so you could check this. But then this contains this set minus this whole set. Right. So yeah, you can check this. This will follow by the definition of the G case. But then you notice that this part is in U, right? Because you're only taking finitely many intersections. And this part is not in U, and this is our assumption. Right. Again, remember the xn's are counterexample to countable completeness. But then you're taking negation of something not in U. So this can be written as something in U intersect with something in U. So the result is also in U. Right, but then the so if this is in U, then the G case will form an infinite descending chain in the ultra power. As you can see, it's really all the same tricks. Right? Exploiting the I guess the structural relation between failure of completeness and the existence of infinite descending chains in the ultra power. And so on and so forth. Okay. So the trick is really to know the definition of G case. Okay. And this part is really just follows from the proof, because we've only worked with omegas, right? So if you look at what we've done here, what we've used, it's all defining things on omega, right? We're working this land. So you just extract what you need from the proof, you can get this final if and only if. Okay. So, okay, moving on. So normality. Oh, there's something else. There's also the derived filter is kappa complete. Okay, now let's show this. The derived filter is kappa complete. All right, so again, the setting is, so we have J from V to M. Critical point of J is at least kappa. And then you have neutral filter W on X, and you have some A in JX, and then now we define we're defining the outer filter W and X given some element in JFX by doing the following. W is equal to those subsets of X that contains the seed. Okay, so this is called a seed. Usually, I think Joe Hamkins came up with the name. But yeah, so claim W is kappa complete. Okay, so this is just a definition chase and elementarity stuff. Right, so so let so proof let lambda, take some lambda less than kappa, let the AIs for I less than kappa be measure one sets according to W. Let A bar be the sequence of the AIs. Right, that is A is a function taking I to the ith element of these sets. Okay, now you observe what do you observe? Let me see. Okay, now A is in the intersection for I less than lambda. Okay, for J, A bar of I. Right. Just follows from elementarity, and then but also that J of the ith item in the sequence A bar is just J of A bar with J of I as input. Right, but I is something less than lambda, which is less than kappa, so that gets fixed. So that is just J of A bar of I. Right, but then this implies that A is in the following intersection. The intersection of J of A bar I, such that I is less than lambda. But then this thing, by our discussion, is just intersection of J of A bar of I for I less than lambda. I'm sorry, for less than J lambda. Right, because lambda is also below kappa, so J lambda is just lambda itself. That allows you to pull J out of the intersection, so that gives you A is in J of this whole thing. Right, but then this would imply that this would imply that imply what we wanted to show, right? So this will imply that the intersection of the AIs is in W, right? Because W is defined by whether you contain, whether J of that thing, well, whether a thing is in W depends solely on whether J of that thing contains A or not. So we just show that it does. Okay. Normality. Okay, so now we are here. Normality. So the claim here is so normality. So claim the derived measure is normal. How do you show this? It's a proof. Let A be in the derived measure U, and let F be a function with domain A to kappa be regressive. Right, I want to show that for a measure one set, for a measure one subset of A, excuse me, for measure one subset of A, F is constant on that set, right? That is what I want to show. And then we notice first that A is a subset, right, by regressiveness of this set, right? But then A is in U, so its superset is also in U. Right. Then observe J of F of kappa is actually less than kappa. Why is this? Well, it follows from this fact here. right? So this set is in U, but then U is the derived measure. So J of this set is in U. I'm sorry. So this set being in U, by definition of U means kappa is in this set. Right, but that is just what it means, right? It means J of F of kappa is below kappa. Okay. And let gamma be this value. Right. Now the claim is this set is the set that we want. What's almost the set that we want. Right. So F maps actually a measure one set to gamma. Okay. But then this is because J of F of kappa is equal to gamma if and only if kappa is in J of this set. Right. But then this holds if and only if J of F of kappa is equal to J of gamma. But then gamma is below kappa, right? This is where the critical point comes in. So J of gamma is actually gamma. Right. So this is what we wanted. Okay. Okay, so let me see. Next one here. Every measurable cardinal is malo. So let me think. Okay, let me show you inaccessible first. So oops. Measurable cardinals are inaccessible. This follows from what I talked about yesterday, right? It's about using reflection, you know. Okay, let me write it down. So suppose kappa is a measurable cardinal. Right. Want to show kappa is regular and strong limit. All right. Regular is easy, right? Because if you break kappa into if you partition kappa into yi's for I less than kappa less than lambda, and each yi has cardinality less than kappa, then by I don't know, so let's say kappa's measurability is witnessed by U, right? Then by properties of U, bounded sets are not going to be in U, right? Because U is a measure and measures large sets. So each yi is not going to be in U. But then use an ultrafilter. This means the complements of the yi's are going to be in U. Right, but then the right, but then the intersection of I less than lambda of the complements is the empty set, right? Because the union of the yi's is kappa, so the complement of the intersection of the complements of the yi's will be empty, right? But then by kappa completeness, this will be in U, so contradiction. Okay. Strong limit. Let me see. Strong limit. So suppose not. Right. fix some function f from the power set of lambda. So fix some lambda less than kappa, and some function mapping. So this means onto surjection, mapping the power set of lambda to kappa. So kappa is not a limit cardinal. Then f is going to be in v kappa plus 1, right? Because all the ingredients of f are there. So every element of f is going to be available at v kappa. So then it shows up at the next level, v kappa plus 1. But then by properties of the elementary embedding, the ultra power stuff, this is actually the same as v kappa plus 1 in the sense of m, right? Where m is just, you know, that m in j to v in the range of the elementary embedding. I mean the codomain. And by now we have j of f is a function j of p lambda onto j kappa by elementarity. Right, but what is j p lambda? Well, p lambda is the power set of lambda is something in v kappa, so that gets mapped to itself. So this is actually just p lambda. Right, but now we notice that if x is a subset of lambda, then f of x is an element of kappa. But what does that tell us? It tells us that, you know, whatever fx is equal to j of fx, because it's something below kappa. So j is the identity below kappa. But then by elementarity, this is j of x j of f of j of x. Yeah. But then jx is also just x, again by j being the identity below j kappa, below v kappa. So this is actually just that. So what have we shown? We've shown that f and jf are actually the same function. Right, so hence f is equal to j of f. Right, so this is a contradiction because f maps onto kappa, jf maps onto j kappa, but we know that j kappa is strictly bigger than kappa. Okay, so this finishes this claim. So let me do malo. So measurable cardinal implies malo. This is also not very difficult. It's also a kind of reflection argument. I just want to show that every club in kappa is going to have some inaccessible cardinal in it. Right, so we know already from yesterday, so we know that the set of inaccessibles below kappa, let me write I, is a measure 1 set. Right, so now it's enough to show that I mean where U is the derived measure. Okay, so now it's enough to show that if C is a club subset of kappa, then C is also in the measure. Right. Why does that suffice? Well, because if the measure, if the ultrafilter extends the club filter, and if the set of inaccessibles is in that filter, right, then it intersects every club set, right? And that would tell us that every club subset of kappa is going to have non-empty intersection with inaccessibles below kappa. Okay, So now this is not very difficult. So how do you show this? Go if C is a club, a subset of kappa, then kappa is actually in J of C. Right. Now, why is this? Because J of C is stretches, right? So it's an unbounded subset of kappa. So when you map it with the elementary embedding, it stretches it past kappa, but with the stuff at the bottom unmoved, right? So this is actually C. So our M is going to think that J of C is is unbounded below kappa. But then M is also going to think that J of C is a club, which means M is going to think that kappa is in J of C. But then whether whether kappa is in J of C or not, this is a delta zero statement. So this is true in V as well. Right, but then by definition, this means that C is in the derived measure. So this finishes the proof. Okay. There's a more direct way of showing this by showing that if you have a filter if you have an ultra filter that's normal, then that's going to contain the club filter. But you know, I take the easy way out whenever I can. Okay. This one here shows some sort of canonical status of the derived measure and the ultra power. So I'm not gonna do the full proof because this just involves checking. So the point is, so for this one, so this is getting a commutative diagram given J from V to M, you could grow the derived measure W, and then you consider the canonical embedding into the ultra power by W. And then you want this K here that makes the whole thing commute. And define K as follows. I mean, if you've seen this, then this is really obvious. You're left with very little choice as to what you can choose. So to ensure elementarity, you want to map K of, so things in here are just equivalence classes of functions, right? So given this function, you map it to J of F of kappa, where kappa is the seed. I think the seed is A here, sorry. So there's some notational inconsistency here. So let me erase this. So of A. Now this is what you want, and then just check. It's not very difficult. Okay. So, all right. So weakly compact cardinals. I'm gonna work with an equivalent definition. So, so here. So weakly compact cardinal. I'm going to go with the definition that I feel is easier to work with. You could. Okay, so let me write this. So kappa is weakly compact if and only if every kappa tree has a cofinal branch. I think I'll also need to say and kappa to the left and kappa is kappa. right? So where a kappa tree is just a tree with kappa levels. Each level has size less than kappa. So it's like in Koenig's lemma, right? So Koenig's lemma says, let me see. So this clause is known as the tree property. The tree property here. So Koenig's lemma. Ooh, that's bad handwriting. Okay. Koenig's lemma says omega has the tree property. Okay. So I feel like this is an easier definition to work with, but I'll go back and forth. So if you want to look at like a proof of all these equivalents, there's a really great answer on Math Overflow by Joe Hampkins. I want to pull that up. I want to send it into the chat, so bear with me here. I had it a moment ago, but then I restarted my laptop. There are like 6 or 7 equivalent definitions, and he very nice the proofs that they are a link the chat. Okay, there are a bunch of different and that Math Overflow page also answers a bunch of the exercises in the weekly compact section. Okay, so this is easier to work with in that it gives the shortest proof that measurable cardinals are weakly compact. So the claim is kappa is measurable, implies kappa has the tree property. Let me write TP. All right. And the proof is short and sweet. Okay. Proof. Let J from V to M witness kappa measurability. All right. Now let T and some ordering on T be a kappa tree. Right now, M is going to think that J, excuse me, JT, and also the ordering sub JT is a J kappa tree. Now pick some element S in this tree such that M thinks that S is on the how do I write this? So the kappa level of this tree. This is guaranteed to exist because, right, the tree, it's a J kappa tree, so it has J kappa many levels. Now let B be its predecessors. Now we could, without lots of generality, we can assume that the tree we started, excuse me, the tree we started with is in V kappa plus 1. Now, because it's all the cardinality that matters, right? You could always replace the points, and by using a bijection and replace what the points in T are. All that matters is this ordering relation. So I could assume that the nodes in T are already available in V kappa plus 1. So then J of T, again, it's same trick when you stretch T and look at below J of V kappa. All right. When T is stretched, the part of T that is below V kappa remains fixed. And also the new ordering, right, of the tree JT, when you restrict to whatever is below V kappa, that's going to agree with the old ordering T by elementarity. Right, but then where do we pick S? We picked S from the kappath level. Yeah. Here, we picked S from the kappath level. So hence E is a co-final branch in T. Okay. Right, so a lot of these proofs are really just going back and forth using elementarity and then exploiting the fact that things below V kappa are really not changed. So that allows you to cheat a little when it comes to, you know, whether you say J of something or not. So all the proofs so far have this flavor. Let me see what's next. So the embedding characterization. So let me do this. Actually, let me just do one direction since the other direction is kind of routine, and it's also available on the Math Overflow page that I just sent. So I think it's the more illuminating direction. I think something that is more relevant to the remainder of the lessons is looking at this sort of external ultrafilter construction. Okay. So let me so the setting is that let kappa be weakly compact, and here I'm using the ultrafilter extension definition. That is the definition in this note here about extending ultrafilters. So we want to show that, what do we want to show? For every transitive M such that kappa is in M and the cardinality of M is kappa. There is another transitive set N and J elementary embedding going from M to N with critical point kappa. Right, this involves an ultrafilter construction. So let me show this seemingly stronger or maybe weaker, depending on how I look at it. It's going to be equivalent. So first, so proof. First, show something stronger. That is, let me call this elementary embedding star. This says for all subset of kappa, there is a transitive set M with A as a member, such that it has cardinality kappa, and here it's closed under sequences shorter than kappa. Right. So how do I prove this? What I do is Let me see. Okay, so given so take so A is going to be in H kappa plus, right? Where H kappa plus is the set of whose transitive closure has cardinality less than kappa plus. So A is obviously something like this. Use the downward Löwenheim's Golem theorem, get the elementary substructure of this, right, such that A is in M. Oh, I'm sorry, I haven't finished writing down the elementary embedding star. There exists N and J such that J goes from M to N elementarily, and critical point of J is kappa. Right. So I wrote this as EE star, but I forgot to write the elementary embedding part. So again, we look at H kappa star. We take an elementary substructure with A in it, right, and size of that is kappa. And also by assumption of kappa, right, we know kappa is and this follows from this kappa to the less than kappa is kappa. Then we also have we could also build M such that M is closed under less than kappa, closed under sequences shorter than kappa. Okay. And take any filter on the power set of kappa in the sense of M, right? Since M satisfies some set theory, so it makes sense to talk about the power set of kappa. Right now, by the filter extension, right, so by definition of weak compact, extend it to a kappa complete ultra filter F on the power set of kappa in the sense of M. Right. Now, all you need to check now is that F is kappa complete, what we get for free, right, from definition. And M is closed under omega sequences, which you also get for free, right, since M is closed under less than kappa sequences. But then these would imply by the proof of our first proposition, right, being countably complete, then this ultra filter, this ultra power of M by F is well founded. Right, so the completeness gives you that there's no infinite descending chain in the ultra power, and then closure under omega sequences tells you that really there are no such sequences, right? Because it might be the case that M doesn't think that M thinks that the ultra power is well founded, but there are other infinite descending sequences out there in V that M fails to recognize, right? So this condition ensures that this doesn't happen. So this tells you that the ultra power of M by F is a well-founded structure, so you could collapse it into a transitive. So this is the end that we want. And then we just take the canonical embedding J from M to N which is what we want, right, for this EE star. So this finishes the proof of EE star. So to get this stronger condition, I mean, to get this seemingly different condition, we use EE star in the following way, right? We want for any transitive set, we could find an elementary embedding like that. Right, but then this is not very difficult. What you do is, so for any M, right, like this here, for any transitive M, you note that such M will be in H kappa plus also, but then this means that you could code M. So we could code M in the sense that we talked about yesterday by, bijecting it with an ordinal, and then, by making it a subset of the of kappa. So we code N by some A subset of kappa. Right now, we just apply EE. Now apply EE star. Right, so this means we find some M bar with A in M bar, and then like above, and elementary embedding J from M bar to some N bar. But then M bar satisfies enough set theory so that A in M bar implies M is actually in M bar. Right, so J restricted to M is what we wanted. Okay. All right. So this downward to L exercise is somewhat tricky. I don't have a full proof of it because I don't get what the hint is trying to tell me to do. But the way that I learned how to do this is the following. I wrote it somewhere else. Sorry, let me give very sketchy proof here. One moment. Okay. Let me maybe hand wave a little as to how you want how you want to go about proving this. All right. So the easiest way, the way I see it, is to prove the following claim. And this is following the presentation in Devlin's constructability book, right? The chapter in the covering lemma has this proposition. So the claim is if kappa has the tree property and kappa is inaccessible in L, then kappa is weakly compact in L. So the outline of the proof is this. Let me see. You want to prove, so you use, so in the conclusion, so use the ultra filter extension definition. All right, so every this and that filter could be extended to an ultra filter. So you start with a filter. Let me think. Okay, you start with a field of subsets. start with F. What is F? It's in L, a kappa complete field, namely algebra of subsets of P kappa in the sense of L. Right, and here kappa complete is also in the sense of L. Right. And now you want to pick lambda less than kappa plus of L, right? To be something large enough, satisfying enough set theory, right? So unmissable, for example, such that in L lambda, the cardinality of F is correctly recognized to be kappa. And then you pick a function witnessing that in L. I'm not witnessing that, I'm sorry. Enumerating the subsets of kappa at that level. Right. We know by condensation at any, well, before kappa plus, right, at any stage of L lambda, there could only be kappa many subsets of kappa, right, at most. So you could fix that by projection, then use C to build an ultrafilter on P kappa intersect L lambda. This is very much like proving the equivalence of the ultrafilter extension definition and the tree property definition of weak compactness. So I'm going to skip that, but the point is you want to build an ultrafilter and then extend it. I'm sorry, then the goal is to extend. Extend. Let me think. The goal is to so okay, here in V. So the goal is to get that ultrafilter into L. Right, and then what you do is, so let's say this ultrafilter is D, then you want to look at the set M, which is the set of functions in L lambda. You're basically using L lambda as your base for building an ultra power. So F kappa to L lambda, right? And then you wanna look at the structure ultra power of M divided out by D, and then you get elementary embedding L lambda to this structure. And then you also want to check that this is transitive. This could be collapsed into a transitive structure, right? So this is actually isomorphic to some L gamma. Right. So then this J is actually an elementary embedding going from some L lambda to some L gamma. Right, and then remember our goal is to get the ultrafilter into L. So you just take the derived measure of J and then check. So this is extremely hand wavy. I apologize for that, but fully written out is very long. Maybe there's a shorter way if anybody knows of doing this using this hint, but I don't know. No. Okay. So this is the idea. Okay. Okay, finally, strong cardinal stuff. Let me see. Okay, I may go over time for like 10 minutes or so, but the strong cardinal stuff is really quick. Modulo some presentation on the extender stuff. Okay, so for example, it's mostly exercises on reflection arguments. All right, for example, kappa is too strong, then kappa is a limit of measurable cardinals. And this is a typical reflection argument. Right, so now M is gonna know, so if J V to M witnesses kappa's two strongness, right, then M is gonna think that kappa is measurable. Why? Because you could take the derived measure and that's going to give you a kappa complete ultrafilter. But then the ultrafilter is going to be in V kappa plus 2. But then that V kappa plus 2 is contained in M. So M is going to see that ultrafilter. So M is going to know that kappa is measurable, but then this would imply that M thinks that there is an MC below J kappa. So pulling it back with elementarity, this would imply that V thinks that there is a measurable cardinal below kappa. Right, again, generalizing a little, generalizing. So this shows that there must be one, right? So if U is the derived measure, then the above argument shows that kappa is in J of this set, the set of measurable cardinals below kappa is MC, right? Which shows that there's a measure one set of measurable cardinals below kappa. Okay. Let me see. Let me move on to the reflection stuff, since this is more interesting and maybe perhaps more useful for later stuff. Okay, this here, kappa strong, then sigma 2 reflecting. This is a very standard argument if you haven't seen it. So claim is kappa being strong implies V kappa is an sigma 2 elementary substructure of V. Okay, how do you show this? So the fact, so we use the fact due to Levy that if kappa is regular uncountable, then H kappa is an elementary substructure, sigma 1 elementary substructure of V. Right, so this way just by absoluteness of sigma 1, and this way you want to take so you want to witness some sigma 1 fact in a large enough structure, and then take a very small elementary substructure inside H kappa, and then use sigma 1 absoluteness to reflect it back to H kappa. So basically this is how to prove the Levy fact. So with this fact in hand, we first prove proof of claim. Let phi have the form sigma 2 exists x for y phi x y z with some free variable z. Right. So now if V kappa thinks, exists X for all Y, psi X, I'm sorry, psi X, Y, C for some C in V kappa as a parameter, then fix A in V kappa such that V kappa, well, basically fix a witness, right? Now use the Levy effect, because now this is a pi one, but then V kappa is H kappa when kappa is a large cardinal. So this is going to be a sigma one elementary substructure V. So they agree on pi one sentences. So this direction is easy. So to really use strongness, it's the other direction. So suppose V thinks exists X for all Y, psi X, Y, C for some C in V kappa. So let A witness this. Nice. So let A be this X. Now we go to some lambda large enough such that A is in V lambda. And since kappa is strong, we can take an elementary embedding capturing the entirety of V lambda with V lambda, a subset of M. Right, then M is going to think that Vj kappa satisfies for all Y psi A Y J of Z. Is that right? Not Z, sorry, JF. I'm getting my variables mixed up, sorry. Let me write Z. So you want to move high enough so that you have the witness. Okay, JFC. Okay, JFC is what I wanted to write. But then JFC is just C, right? Because C comes from V kappa. So now M is gonna think that Vj kappa thinks there exists some X for all Y, psi X, Y, C, JC. Right, but then now you could pull it back to V. V is gonna think V kappa thinks there exists X for all Y, psi X, Y, C. But then this whole thing is delta one. So
But
this is actually true.
Is that M sync Vj lambda sync this universal sentence true?
Oh yeah, yes. I skipped a little. So you want to first say V lambda thinks that, but then by downward absoluteness, Vj kappa is going to think that. Yeah, thank you. So I skipped something. Yep. Okay. So the trick again is to go far enough so that whatever you want. So with these say super compact, strong, where this is sort of kind of like a for all, or this and that, the usual trick is to go far enough, high enough in the von Neumann hierarchy or what have you, and collect what you need and then pull it back to V. Okay. And what else? So the other exercises in this, they all depend on the theory of extenders. Now, this one, for example, this one, for example, and this one. The point is, so I'm not going to have time to go over all the intricacies of extenders, But if you want to read about extenders, YEC, chapter 20, section 28 is about extenders, and Kanamori, chapter 26. It's also a presentation of extenders. The point is, so the point, so in here, kappa being a strong cardinal is defined using elementary embeddings, which is a public class object, right? The point is with extenders, you could write kappa is gamma strong is in delta 2 fashion, right? In the variables kappa and gamma. All right, so it's delta 2. So for instance, that allows you to solve, this here, right? Is, I'm sorry, not this. This. All right, so if you're lambda strong in a lambda that's sigma 2 elementary, that's sigma 2 reflecting, then for any ordinal, so for any ordinal alpha, so there cannot be a least ordinal where you are not, there cannot be a least ordinal alpha where you are not alpha strong, right? Because otherwise it's going to be reflected by lambda to something down below, contradicting the assumption that kappa is lambda strong, right? And all the heavy lifting is done by the extenders, allowing you to express kappa is gamma strong in the delta 2 fashion. Okay, so that's about it. So all the other ones here in the strong section, in the strong cardinal section could be done by alluding to this point very easily. So, okay, any questions?
Do you have a question for Jason or for the lectures yesterday?
Yeah, if
So
there's
maybe...
any feedback or something that you would like me to communicate to Gabe, I mean, you're welcome to do it yourself also. But if you're shy or something, I don't know. Not that I'm a particularly forward person, but you know, I can help.